All right, thank you very much. And thanks for the invitation. I'm happy to have a chance to speak here. What I want to talk about is, as you may guess from the title, a question of what the internal language is of a diagram of toposes, rather than if just a single one. If we'd like to be able to use something like the internal language of one topos to instead reason about not just one topos, but several of them connected by some geometric morphisms and transformations. So that's the goal here, but I'll sort of sneak up on it for a while. First, I want to sort of review some things about ordinary internal languages and the sort of ones that I'm going to be using, and then we'll sort of move in the direction of diagrams and a particular example first. So I expect everyone here is more or less familiar with this, but just for comparison with something else later, I want to put this up here. So the traditional sort of Mitchell-Benabou internal language of a topos is a higher order logic. So we have some types, and we have operations on types. We have a product type and a function type, usually, and things like that. And then these are interpreted into a topos as objects, and operations on objects like products and exponentials, and the terms belonging to a type represent morphisms. And then we have propositions, which may be elements belonging to the subobject classifier, or depending on how the logic is presented, they may be some separate thing. Belonging to some context of variables in types, which represents either a morphism into the subobject classifier or equivalently a subobject of the product object corresponding to that context of variables. And then there are operations on these things that happen sort of fiber-wise. So this is great, and it's useful for a lot of things. And the sort of higher order language is not it's not sort of the set theory, which most mathematicians are used to thinking of as the way we do sort of foundations of mathematics, but it's enough to encode basically all mathematics that people do, but it's a little bit awkward occasionally. And so here's an example of one place where it's a little bit awkward, because if we want to actually define a category inside of higher order logic, basically the only way to do it is to have a single type of all the arrows. So we have a type of objects and a type of arrows, and then source and target functions that map the arrows to the objects. And that's okay for some purposes, but sometimes it's more convenient to have a separate type or set of arrows between any pair of objects. And if you want to do this in a type theory rather than a set theory, then you need what's called a dependent type theory, where you can have types like this hom type, hom c of xy, that involve variables belonging to other types, rather than the sort of simple type theory used in higher order logic. So, the dependent type theory turns out to be also really useful, almost maybe necessary to formulate a usable internal language for higher toposes, infinity toposes and this sort, and this is sort of where I came to it from, but it can be more convenient in the one categorical version. So in dependent type theory, if we use that instead as an internal language for toposes, then what we have is we have not just propositions that depend on variables, but we have arbitrary types depending on variables. And then in a now, instead of a proposition that's interpreted by a sub-object of A cross B, then a type in this context of A and variables in A and B is interpreted by an object in the whole slice category, anyway, an arbitrary object in the slice category over A cross B. There's a little slightly more complicated version, right, because the types in the context could depend on each other. So if I have the second variable y depends on a b, which is a type that depends on the first variable a, then that gets interpreted by an object of a slice over the interpretation of that whole context, which is really just the total object b, because b is a type that depends on a, and so it lives in the slice over a. And that if B doesn't depend on A, then we sort of make it depend on A trivially by pulling it back to the slice over A, and so that's how we get the product A cross B. And we can do that for arbitrary length of context. And then just like there are operations on propositions, logical operations of conjunction and disjunction and implication and so on, we have operations on types, which sort of generalize these, and also the ordinary operations on objects. So there's the dependent function type, which has many different names. Sometimes it's called a pi type. Here's one notation for it that I've written over here, which is the one used in some proof assistance, where we write A arrows B, but now we put a variable x on A so that we can use it in the codomain B of x. And that represents the right adjoint to pullback, sometimes called a push forward between slice categories in a topos. And there's an equality type, which is represented by a diagonal, just like the equality proposition in higher order logic. And we can identify the propositions as sitting inside the types as just the types which have at most one element. So whenever I have a family of types over A, then for any point and any 2 points over A, they're equal. And so that's basically saying that your object of the slice category is subterminal in the slice category. In other words, it's a proposition, it's a subobject. So I'm going to be working with this dependently typed internal language. Just as a brief mention of universes, right? So in higher order logic, propositions are equivalent to terms that belong to the subobject classifier in whatever context you're working with, sort of the object of propositions. And in type theory, dependent type theory, the types can similarly be considered to be terms belonging to a universe type. It's a little bit more complicated because we can't have all the types belonging to the same universe for this sort of Russellian paradox reasons, but we can still do it, and we have sort of a hierarchy of universes. In order to interpret that in a topos, you need the topos to have universe objects. Okay, not every elementary topos has universe objects, but Grothendieck ones and realizability ones do, so it's not a huge restriction. But we also don't need universes. We can have dependent types without universes just by having types in some context as a primitive object in the syntax. So that's all I want to say about universes. I care about dependent types, but the universes won't really matter today. Using dependent type theory as an internal language for toposes is a little bit more complicated than for higher order logic in terms of the formalities of the interpretation. And I don't want to get into the details of this, but I just want to mention it briefly because part of it is going to come back later. So the issue is basically that substitution into a type corresponds to pullback of things in a slice category. So just like in the higher order logic, substitution into a proposition corresponds to pullback of subobjects, pre-image of subobjects. The same thing is true for, a similar thing, analogous thing is true for objects in the slice categories and substitution in dependent type theory. But there's a little bit of a difference here because substitution is strictly functorial in the sense that if I substitute something for y, which involves a variable x, and then I substitute something for the variable x, that's strictly syntactically the same as sort of substituting into my first function term and then substituting into the whole thing. But in a category, usually pullback is only pseudo-functorial. If I pull back along f and then along g, that's only isomorphic to pulling back along the composite f and g. And in the case of higher order logic, that's not really a problem because we can consider subobjects up to isomorphism. We can just sort of say subobject is an isomorphism class of monomorphisms, and then it doesn't matter. But in dependent type theory, it kind of matters because we can have non-trivial isomorphisms or automorphisms of objects in slice categories, and so we have to sort of keep track of this. So usually the way we deal with this is something like the following. We use an intermediate structure between the syntax and the semantics. So instead of just going directly into a category or topos, we have this thing in the middle that we call, hey, there are lots of different versions of it that go by slightly different names. One of them here is what I'm calling a comprehension category. I'm not even giving you a formal definition, but basic idea is it has a category which is like your topos. When we think of the objects of that category as being the contexts, in the type theory. And then the types, which we were sort of thinking of as sort of belonging to some slice, but instead, formally we represent them not by objects of the same category, but by elements in some indexed category over that base. So either like a pseudo-functor in the cat or a fibration maybe over the base, depending on how you formulate it. Every object in the base, which is, if you think of it as like a context, has a category of types in that context, semantic types, not sort of syntactic ones, whatever they are. And then we basically, the important operation is that we can extend the context by a type to get a longer context. The idea is we start from giving a topos, we build a comprehension category by just taking the types in some context to be the category of the slice category over that object. And the functorial actions by pullback, that's only a pseudo-functor, but then because we've sort of separated out the pseudo-functor from the category, then we can apply a coherence theorem to make the pseudo-functor a strict functor, so that pullback will be strictly functorial. And it won't, the fibers won't be now literally the slice categories, but they'll be something equivalent to the slice categories, and they'll have strict pullback. And so there's a bunch of references here. Right? The original interpretation of dependent type theory was given by Seeley, but he didn't completely satisfactorily deal with this pullback problem. And then Martin Hoffman did that in a decade later by giving one sort of coherence theorem, and then later there have been other coherence theorems as well. The particular one that given by Lumsden and Warren is particularly useful for higher toposes because it can deal with things a little bit fancier. But again, I don't want to get into any details. The main idea is we have this intermediate structure called the comprehension category that we use for the interpretation. So that ends my review of the internal languages for a single topos and the dependent type theory version of it that I'm going to use. Maybe I should say, anybody who wants to ask a question in the middle, if anything is not clear, please do let me know somehow. I don't know whether I'll be able to hear you directly, but get it to me if you need to. Let's see. So next, I want to talk about how we might go about trying to find an internal language for a diagram. So sort of an example. So what do I mean by a diagram? Well, so formally, I mean I've got some two-category M, which is the shape of the diagram, and then I have a pseudo-functor from that into the two-category of toposes and geometric morphisms and transformations. And there are many different contexts in which we might be interested in this. I've listed a few here, which are basically just slight enhancements of a single topos, but it's a single topos in this case with extra structure. So, for example, we might want to talk about a topos over a base, which is just two objects and one morphism between them, two toposes and a geometric morphism. But now maybe I want to be able to talk about not just objects of one topos, but how they're related to objects of some base that it lives over. Or this geometric morphism might be fancier in some way. It might be a local geometric morphism, or a connected or totally connected here is the one that can be thought of as something, a diagram happening inside the two-category of toposes. Maybe I should briefly say there are sort of fancier versions of this that you can try to deal with diagrams of form functors that aren't part of geometric morphisms in general, but this is sort of the simple case that I want to talk about today, and perhaps one of the more interesting ones. So a local topos or a totally connected topos can be interpreted as a geometric morphism which has a left or a right adjoint with some, which is sort of a reflection or co-reflection inside the two-category of toposes. More concretely, that's the same as saying that either the right adjoint part of a geometric morphism, the direct image, has a further right adjoint, or else the adjoint part, the inverse image, has a further left adjoint. So the question is, again, can we find an internal language that allows us to talk about all of the toposes in this diagram and the morphisms between them at once? So let's look at the particular case of a local geometric morphism. Was sort of one of the first that was considered historically. So this is in the context of something like a higher order logic. But now we have a local geometric morphism, and the logic that we can interpret is not ordinary logic, but some kind of a modal logic. There are many different kinds of modal logic nowadays, but the traditional one has two new unary propositional operations called modalities, box and diamond, which are traditionally interpreted as saying box phi says that phi is necessary, and diamond phi says that phi is possible. Audi and Birkedal showed that if you have a local geometric morphism, then we can interpret traditional modal logic, more or less of this sort, as follows. So we take the types to be the objects of the base topos S, and we take the propositions in some context to be subobjects of the corresponding discrete object in the upper topos E. And then we have the box and the triangle operators, which are given by round-trip monads or comonads on the upper topos, right? So the F star has both a left adjoint and a right adjoint in a local geometric morphism, and so we apply those to the subobjects, and acting on the base object, because it's of the form F star of A, it's sort of, both of those adjoints fix that object. If I sort of map back down to S and then back up again, I get the same thing. And so you can think of this box as sort of like a topological interior, and diamond is kind of like a topological closure, if you feel like it, or equivalent. You can also think about box as sort of a relative discrete co-reflection. If you think of as E as some kind of category of spaces of some kind, then you can think of box as saying, take the same set of points in your space and equip it with the discrete topology, and diamond is equipped with the indiscrete topology, left and right adjoints to it's a forgetful operation. Okay, so this is nice, and you can do some things with it, but it's a little bit limited because the objects, the types, are only represented by objects of the base topos, and the only thing we can say about the upper topos E is that it has, we're talking about as subobjects. So what we'd really like is we'd like to be able to reason about objects of the upper topos E as well, and the actions of these functors on arbitrary objects. And so it's natural to try to use a dependent type theory instead. So we have, now we have modalities, and a modal dependent type theory. We have modalities that act on types and not just on propositions. So if we have types that represent objects of E, then we should have a sort of a box, a discrete co-reflection that acts on types, and a diamond, an indiscrete reflection that acts on types as well. But now, because we're in dependent type theory and types can be in a context, then we have to ask, well, what is the context of a box type or a diamond type? If I have, and in general, of course, it's going to be some arbitrary context, but the same ideas already arise if I just have a context of a single variable. If I have a single variable x belonging to type A and a type B in that context, then I want to have box B. What is the type of box B? So semantically, this is a little bit tricky. Semantically, basically, I want to say that it belongs in context of box A. And so I have B, which lives in the slice category over A, and then I apply box, which is this round trip comonad. It maps from E down to S and then back up to E again. And they're functors, so they apply to the base object as well as the top object. So B lives over A, I map it down and back up again. Now I get box B living over box A. Right? And so that's sort of the naive answer to say that we should do this in syntax too and apply box to the context. But it's just kind of problematic for a bunch of technical reasons. So one of them is that if I have B that depends on A, on a variable x, and then I apply box of it, then I don't really have the same variable anymore because x was a variable belonging to A, but now I have some new variable, x prime, that instead belongs to box A. And you might say, well, it's just use the same letter variable, but I mean, inside of the syntax of the type B, that the reason that syntax makes sense is because x is a variable belonging to A, but now I have a variable belonging to box A instead, and so somehow I need to use that variable differently. So it's not clear exactly how to write this type syntactically. Similarly, a similar sort of problem is now if I do this and I get a type in context box A, and now I want to substitute for that new variable x prime, so I have some function from some other type C to box A, then there's got to be some way to do that, because I have to be able to substitute in syntax, and that's going to be sort of a pullback. But now I sort of have my box B living over box A, and I have a map into it, and I pull back, and I get sibling living over C. But now I have that's sort of a boxed type. Syntactically, it should be box of something, but it doesn't live over a box of anything anymore. It lives over this other thing C. So we get sort of something, this box operation syntactically that sort of boxes the context also is not sort of closed under substitution, which is kind of a problem. But in fact, these problems, the reason that there's problems is that we really asked the wrong question in the first place. So if we sort of think about the way type theories are defined, one of the ways that they're constructed formally is so that they can be implemented cleanly in a proof assistant. The type checker for a proof assistant actually doesn't want to ask this question anyway. The type checker wants to ask a different question because as it goes along trying to type check some syntax, it knows what the context is currently, and it sees something like box of whatever. It's type checking from the outside in. It sees the box, and it says, okay, I'm trying to type check this box of something in some context. But now, okay, so I saw a box, that means I'm going to be applying the box rule for type checking a box, or the rule for applying box to some type. But now I'm going to go on, after noting that I'm going to apply the box rule, and type check the inside of the box, the thing that's getting boxed. And so I need to modify the context of the box to get the context in which I will now type check the thing that's getting boxed. So the question we should really be asking is, Not if B is a type in context A, what is the context of box B, but rather in order for box B to be a type in context A, in what context does B have to be a type? Okay. So that's the new content, the question that we should be asking. One answer to that question in the case of a particular case of a local geometric morphism leads to this thing that, that I called spatial type theory a few years ago. So the idea here is we sort of, we have the boxes living in the context, but we don't represent them syntactically by saying that we have a variable belonging to box A. Instead, we have a different syntax for what you might sometimes call a boxed variable or a crisp variable or a flat variable, a variable that is sort of syntactically associated only to A, but semantically the A has a box on it when we interpret that semantically. So I'm writing this with a double colon. We have ordinary variables in type A, and then we have double colon variables in box of A. And maybe just for emphasis here, all the types in this particular situation will change later, but for now, all the types are objects of the top category E. There are no types that represent directly objects of the base category S anymore. So all the types are the same kind of type, but we have two different kinds of variables, one of which semantically corresponds to the actual object and one of which corresponds to the box of the object. Box is idempotent in this local case, right? It's an idempotent comonad, so it's, we don't have to worry about how many boxes there are on something. So now if we have a context like this, that's where we've syntactically labeled which types belong to boxed types, then we can do this thing which I'm writing as dividing by box. There are different syntaxes for this. Sometimes it's written as a lock operation or with box and braces or something like that. Whatever it is, it basically says we take a context and we throw away all the ordinary variables and remember only the crisp ones, only the boxed ones. And so that's kind of like applying box to the context, but instead of, if we sort of say, if there are any types that aren't already boxed, we'll just sort of throw them away, ignore them. And then the ones that are already boxed, we can keep them because box is idempotent, so boxing them does nothing to them. But it's actually sort of going in reverse. Basically, it's saying like the box of the thing, well, what part of this context could have already been boxed? And the ones that are ordinary variables couldn't already have been boxed, so we'll get rid of those. And the ones that are crisp sort of are already boxed, and they might as well have been boxed if something already boxed. So that means that we can answer the type checker this way, that for box B to be a type in context gamma, it suffices for B to be a type in context this gamma divided by box. Let me do a little bit of the example sort of categorically so we can see how that works in terms of slice categories. So if gamma is sort of the simplest non-trivial case where we have one crisp variable and one ordinary variable, so categorically that means as long as there's no dependency, then that means that this context is box of A times C, Cartesian product here, whereas gamma divided by box just has the crisp variable, and so semantically that's just box of A. So this divided by operation, at the moment it's a syntactic operation. In a minute it'll be a semantic one. So then if we have a type living over box A, because that's what this rule says, it suffices for B to be a type in context gamma divided by box, which is just box A in this case. Then we can apply box to it semantically. We sort of forget down to ES and then move back up to E, and now box B lives over box of A, which again is idempotent, box is idempotent, so this is really just equivalent to living over box A. Okay, so that's great, but now we want to get something over our original context gamma, which is box A times C, but we can just pull it back along the product projection. Or syntactically, that's called a weakening, pulling back to adding some extra variables. And that gives us the type in context box A times C, the original context gamma, which we're going to call box of that original type B in the syntax. So the syntactic box operation is now given by semantically applying that comonad and then pulling back to add these extra variables that we threw away. And then they could do a similar thing for diamond. There's a divided by diamond operation which makes all the variables crisp, even if they weren't already. And then we have a similar rule for the diamond operator. that for diamond B to be a type in context gamma, it suffices for B to be a type in context gamma divided by diamond, and then what this looks like semantically is if I have the same gamma, then gamma divided by diamond has both variables crisp, so semantically that's box A times box C, or box of A times C, because box is products. And so if I have a type in that context, gamma divided by diamond, living in for box of A times C, then diamond of it lives over diamond of box of A times C, but the thing about the interaction of these things is that they sort of eat each other, so if you box something and then diamond it, that's the same as diamonding it, just diamonding it. And so now we have box B over diamond of A cross C, and we could pull it back to the original context, because sort of diamond, box is the comonad and diamond is the monad, so you have a map from box to the original object to diamond, so we can pull it all the way back. Okay. So that gives us an internal language of dependent type theory for a local geometric morphism. And this basic idea of these sort of crisp variables, although they weren't called that, goes back at least to Penning and Davies' 2001 judgmental reconstruction of modal logic type theory. And then Dan Licata and I worked out a slightly more general version of it. And I wrote this paper about crisp type theory used for various sort of synthetic topology and higher type theory. But this basic idea works for any local geometric morphism. But it's a little bit tricky to generalize directly because it depended on saying that we're going to take all the types to be objects of E. For a general diagram of toposes, we need objects that live in every topos. It's sort of been, it's going to be kind of limiting if we could only pick one of those toposes and have the types only live in that topos. So what we do is we have a separate mode of types for each object in our domain category P, and so for each topos. So every judgment in our syntax, every notion, every type, every term, every whatever it is, happens at a particular mode. We have an internal language for each topos separately. We have contexts and types dependent on those contexts. But then for every morphism between these toposes, we have a modality that makes types in one mode into types in another mode. Okay. And we're going to have a similar, we'd like to sort of implement this in a similar way to say that for every modality, there's a sort of a division operation, which allows us to write a rule like this in order for I'm calling this modality box mu for each morphism mu in our category M. And the rule is going to be something like for box mu to be a type in one context, which lives at some mode, then it suffices for our original type to be a type, some other mode in this divided context that goes backwards. And I didn't write this down here, but actually, really, there should be two modalities for each morphism in M, because each morphism in M gives us both the inverse and the direct images in a geometric morphism. And so we want to represent both of those, so we should really have a box mu and maybe also a diamond mu, each of which with their own division. But the emphasis is that there's this division operation, and what is it? We actually have to think a little bit more deeply about even what a context is, right? In order to answer that question. So in ordinary Martin-Left-dependent type theory, the kind that I was been talking about originally, the contexts syntactically are inductively generated. So there's an empty context, and then given any context and a type in that context, then we can add that type to the context with a fresh variable and make a new context. And every syntactic context is obtained by extending the empty context successively by a list of types, variables belonging to types. So if we modify this, we basically, the solution to this that was advanced a couple years ago by Gratzer, Kavvos, Nuyts, and Birkedal, they call it MTT, or multimodal dependent type theory. The contexts are inductively generated, not just by starting with an empty context and adding types, but also by these sort of division operations. So they say there's an empty context at each mode, and then whenever I have a morphism and a a context in one mode, then I can get a context in another mode, sort of going backwards. And then I can also add variables, add types to the context, but this adding things is a little bit complicated because of what mode the type has to live at. It's basically a generalization of this idea of a crisp variable, so that for every sort of modality that you might want, there's sort of a syntactically labeled version of variables that sort of appears differently in the context. But the context then has to be divided by that modality in order to in order for the type to live in that divided context and then extend the original context. But the important thing here is that this gamma divided by mu is an inductive generator of the context. So rather than being an operation on contexts, like it was in spatial type theory where he said I have this context and then I make a different context by sort of actually going into the context and pulling out the non-crisp variables. Here, I'm just going to say this context with the symbol divided by mu at the end of it is a new context, and I'm going to give rules for the way that thing behaves. And there's a reason for doing it that way. If you sort of really, if you've been sort of just only barely hanging on with the dependent type theory and syntax and context, you can zone out for this slide. But I wanted to say a little bit about why we do it this way. So so here's this is why it's an inductive constructor rather than operation. Why is that? Well, this has to do with the meaning of this division operation, and that's characterized by the rule for using variables. So if I have a context with some variable which is labeled by mu, and then I have divisions appearing in this context theta at the end, then in order to use that variable, I have to give a two-cell which relates the mu that it was labeled by to the composite of all those divisions appearing after it in the context. And that it's kind of a delayed version of saying what the division operations do. They sort of take away the variables that they don't want to be there, or they modify their annotations. But we sort of delay it until we actually use the variable. And the reason why we have to delay it is, in general, this choice of a two-cell, we might need to make different choices at different places, even in the same context. So we can't sort of decide right away when we do the division what the two-cell is going to be and go in and modify the context. We have to wait. Sometimes there might be a unique choice, and that's the case in spatial type theory. There's a universal choice called a left lifting in the two-category M, but in general that isn't possible and we have to wait, and that's why this division has to be an operation, a constructor of context rather than an operation. Okay. If you zoned out, zoned back in, the point is, in the syntax of MTT, each morphism that induces a modality has both an operation that goes from types in one mode to types in another mode, but it also on types, but it also has an operation that goes backwards on context, this sort of division thing. And we can't really get rid of it, so we need it. The sort of naive way to interpret this type theory into semantics requires this operation, division on context, to actually exist in the semantics. So what should that operation look like? We can get an idea of what it should look like by looking at the rule for defining terms belonging to these modal types, these box types. The rule for defining terms of a box type is similar to the rule for defining the box type itself. If we want to define an element of the box type, a term in the box type in some context, it suffices to have some other term in the divided context, in the original type. And if you look at this as sort of a rule here, so I've written this as an inference rule, it basically says if I have a morphism 2b, right, in general, if B lives in context gamma, then this is a sort of a section of that object of the slice category. But if you think about the non-dependent case, you can think about a term in context in type B as in context gamma as a morphism from gamma to B semantically. So this is saying from the top, if I have a morphism from gamma divided by mu to B, then I can get that from that. I can get a morphism from gamma to box of B. And so that should suggest that division is left adjoint to box. And this is basically right. There's some details with involving dependency, but basically it's right. And so the theorem of GK and B is that you can interpret their type theory MTT. If I have any diagram of categories, sort of sufficiently good categories, usually they're going to be toposes. But the point is here, we're looking at diagrams of categories and functors here, where each category is a topos and each functor has a left adjoint. But the functors here are supposed to represent both the inverse images and the direct images. Each of them is going to have a modality. In MTT, each modality needs its own division operation. And so, in consequence, what that means is if I have instead some diagram of toposes, this category, the diagram E here from L to topos, where each geometric morphism has two functors in it, so that gives me a functor into cat that's defined on a two category that I get by freely adding left adjoints to represent, to correspond to the inverse image functors. Then I can interpret MTT, this type theory, in this diagram over this two category with these left adjoints added to be the inverse image functors, but I need extra left adjoints to exist in the semantics to represent these division operators. So in other words, each of these geometric morphisms has to be essential. It has to have a further left adjoint to its inverse image functor. This is basically what I already said. Each geometric morphism is an adjunction, so it induces a functor to cat, where I represent both the direct images and the inverse images. The direct image functors already have left adjoints, namely the inverse image functors. So dividing by a direct image functor semantically is going to be equal to just applying the inverse image functor. But then I need them to be essential to have a further left adjoint to the inverse image functor to be the division by that operator, corresponding to that diamond-like modality. Okay, so that's okay, but it's kind of annoying because we'd like to be able to interpret geometric morphisms that aren't necessarily essential. So that's the direction where we're kind of trying to go to fix this problem. Okay, so what can we do if the geometric morphism is not essential? The key idea is that this left adjoint acts only on contexts and not types, whereas the important part of the internal language tells us that we care about acts on types and not contexts. And we've already seen a place where we separate the context from the types in interpreting dependent type theory, where we have this comprehension category thing. We have a base type category of context, and then we have families of types, categories of types living over those bases. So that actually gives us some extra unused freedom because we don't have to start with the comprehension category, where the base category of context is the same as the one in which we take slice categories to get the types. We can do something more fancier, and that is going to let us solve this problem. And so there are different ways to do it, but here's sort of a simple, more topos theoretic one. If I have a topos, E, and I have a topology on it, so it has a subcategory of sheaves inside this topos, a left exact reflective subcategory with a sheafification functor mapping the ambient category to the smaller category of sheaves. So it could be, usually it's going to be pre-sheaves on some site and then sheaves on that same site living inside it. Then I can define a notion of what it means to be a relative sheaf. It's an object of a slice category, B in a slice over A. A is not necessarily a sheaf, but sort of B is a sheaf relative to A in the following sense, that if I sheafify both of them, then I get a naturality square, and that's a pullback. So B is sort of equivalent to its sheafification as it could be while still living over A, which is not a sheaf. It turns out that the category of relative sheaves over A is equivalent to the category of sheaves over the sheafification of A. So we can use this to sort of say things about the sheaves, right? Our type theory reasons about types. The contexts that appear in practice are built out of types in syntax. If we take the base category to be the whole topos E, the whole topos of pre-sheaves, but then we say that a type in context gamma is a relative sheaf over gamma, even if gamma isn't a sheaf, then our type theory will really be only saying things about the sheaves, even though we've got this base category, which is all the pre-sheaves. All right, so how does this solve our problem? Suppose I have a geometric morphism. Let's go back to the case of a single geometric morphism, and suppose we have a couple of sites presenting our toposes, and we assume for the moment that we can present this geometric morphism using a cover reflecting functor. So not the ordinary notion of morphism of sites that preserves covers, but the kind that lifts them. Sometimes it's called a comorphism of sites, and it goes in the same direction as the geometric morphism. itself, from the site of E to the site of S. And then being cover reflecting means that it induces a geometric morphism where the direct image is right con extension and the inverse image is substitute pullback along this functor composed with sheafification. And then, so that's how we induce this operation on the sheaves, and we get any geometric morphism, we get a geometric morphism like this, but in fact, if we then instead look at the pre-sheaves, we do have an essential geometric morphism here because we also have left con extension. In general, for a cover reflecting functor, the left con extension doesn't descend to sheaves, but it does act on the pre-sheaves. And so if we think about the pre-sheaves as being the categories of contexts in this comprehension categories, then we'll have an essential geometric morphism there, which we can use for the divisions, and also we'll have the types that are sort of the sheaves. So our goal then which should be, well, let's try to find sites for a geometric morphism such that it's presented by a cover reflecting functor. And this has been known for a long time how to do this. Merdijk did it by considering E as an S topos presented by an internal site in S, and then externalizing that site relative to some site for S to get a nice sort of semi-direct product site, whatever you want to call it, Gordon deconstruction site. And that gives a cover reflecting functor. Yeah, I'm going to use a more explicit comma category construction, which is in Caramello's paper, denseness conditions, morphism equivalent to the topos, and I think it generalizes better to the case of an arbitrary diagram. So I just want to go over this briefly, construction briefly, and then we'll go on. We'll do the general version is more complicated, and I won't be able to explain all the details of the general version for time reasons. But it's basically going to be very similar to this. So what do? We start by finding subcanonical sites with finite limits for the two categories, for the two toposes, such that the inverse image maps the one site into the other site. So considering the sites as subcategories of the toposes. And I'm going to write F dagger for the inverse image functor restricted to the sites, to the generators. And as usual, this goes now in the opposite direction. Right? So this is not going to be our cover reflecting functor. And in this case, I can keep one of the sites the same. I'm going to keep the site for S, the base topos, to be the same, but I'm going to replace the site for the upper topos by the comma category over this F dagger. So its objects are something, a site object of the site for the base topos, and then something living over that in the site for the total topos. And so this has a forgetful functor down to the original site for the upper topos E, which has a fully faithful right adjoint that sticks in the terminal object of the site for the S. And so when we take presheaves on this forgetful functor, then we get an adjunction in the other direction between presheaves. So this functor going backwards from presheaves on B, the original site for E, up to presheaves on D, this new comma site, it's a fully faithful left adjoint. And it also has a further left adjoint, left con extension, which is left exact since U is left exact. And so that exhibits presheaves on B as a left exact reflective subcategory of presheaves on D, in other words, a subtopos in the geometric sense. And we have a topology on B, which represents E as a subtopos of presheaves on B. So I compose those reflections, and I get E, the original topos E that we care about, as exhibited by sheaves for some topology on this slice, this comma category site D, sorry, that I'm calling D here. So there's some topology on D whose sheaves are E. So now I've got these new sites for these two toposes, and I want to relate them by the functors that I'm interested in. So there's this F dagger from C between my original sites, and I can lift that in a straightforward way to the new site, the new comma category site, which is all still sort of an ordinary morphism of sites in that direction because the topology is created by this functor U that maps down to B. So it induces the same geometric morphism, but now it has a left adjoint because I also have a functor from this comma category down to the site C for S, which just picks out the comma category has an object from both categories in it. So I just pick the other one. That gives me this functor L from my new site for E down to my old site for S, and that's left adjoint to this functor between sites. And so the left adjoint of a cover preserving map between sites is cover reflecting, and it also uses the same geometric morphism. So this is what we wanted. So now, using this original site for S and this comma site for E, we get this, it's actually an adjunction between the sites, and the left adjoint is cover reflecting, and so it induces this essential geometric morphism of pre-sheaf categories, and thereby a way to interpret multimodal type theory using these comprehension categories where we have the base categories are pre-sheaves, and for the fiber categories are sheaves, and so the type theory is really only telling us things about sheaves. Okay, so in the last 5 or 10 minutes here, I want to say a little bit about how we generalize that to arbitrary diagrams. Okay, so we want to do the same thing for all the geometric morphisms in a diagram, so that we can interpret this type theory over this two category that has both adjoints in it. So we want to find sites of definition for all the toposes in a diagram at once, so that all the geometric morphisms in the diagram are presented by cover reflecting functors, so that we can present them by this essential geometric morphisms. So the basic idea is that a comma category is a very special case of an oplax limit. Okay, so what do? We're going to start with a diagram. We're going to do the case where we have a finite diagram. This is sort of the only case that we really know how to deal with in general so far. So we have a bunch of geometric morphisms in this finite diagram, and we can, in the classical way, we can find subcanonical sites with finite limits for each of them, so that each inverse image functor in the diagram maps the site of its domain into the site for its codomain. So basically, I like find the generating set for each topos and then close it up under the images of the inverse image functors and also the finite limits, so that we still have small sites that way, because it's a finite diagram. So then now we get a diagram of the sites, but I can just consider it as a diagram of finite categories with finite limits and left exact functors. And I'm going to write the functors in this diagram again with the dagger. So mu dagger is the functor between sites induced by one of these maps. Okay, so now we're going to take some oplax limits, and the oplax limits are indexed by the lax slice 2 category. So the objects, so if I have my 2 category L, which indexes my diagram, I pick an object in it P, and it's considered the lax slice under P. So the objects of this category are the ordinary things that you would have in a slice category, some other object Q in a map from P to Q. But the morphisms are not commutative triangles, but triangles inhabited by a 2 cell in a particular direction. And then the 2 cells in this slice 2 category are 2 cells that sort of make some diagram 2 cells commute. And there's a forgetful functor down to L, which just forgets the P and just remembers the codomains of these things. So that means that any diagram on L can be pulled back to give a diagram on this slice. Okay. So in the case of the ordinary single geometric morphism, we were able to get away with just replacing one of the sites and leaving the other one the same. But in general, we're going to have to replace all of them. Okay, so we've got this diagram C. I'm going to replace it by a diagram D, where at some particular mode P, dP, the new site, is the oplax limit of the diagram, the original diagram pulled back from L up to this lax slice under that object P. Okay. So what that means concretely, an oplax limit of categories is basically an element of an object of that oplax limit says I have an object in each of those categories, but rather than having to be equal, as in an ordinary strict limit, when we map the transition functors, or isomorphic, as in a pseudo-limit, they're just related by a morphism whenever we do a transition. So what this means concretely in this case is an object of dP is for every morphism out of P, I have an object in the codomain site for that morphism. And then for any triangle inhabited by a 2 cell, I have a morphism relating these 2 objects, one of these objects, to the dagger of the other one. And then there's sort of functoriality and compatibility axioms. And sort of the details of this are not really important. The thing I want to emphasize is that it generalizes the slice category. So if the diagram I started with was a diagram on the category with the two objects and one morphism between them and identities, then if I look at the lax slice 2 category under this first object P, then that lax slice category 2 category is equivalent to my original 2 category L. And DP, this new thing, is this comma category that we did in the original case. So if we think of unravel this construction a little bit, according to this definition up above, its objects have 2 objects, because this lax slice has 2 objects corresponding to the identity morphism of P and this non-trivial morphism nu. And so the objects of the oplax limit, each of them has 2 objects, one in P for the identity and one in Q for nu. And there's a morphism between them because there's one of these triangles inhabited by a 2-cell. In this case, the 2-cell happens to be an identity. So here's the triangle. And so this is a map from the object in CP to the image of the object in CQ. And that's all there is in this case. And so it really just recovers this comma category. For this value of L, if I do the lax slice on Q, then it's just the terminal category, and the oplax limit is just the original site CQ at that point. And so that explains why, in that case, we didn't change the site for S in the case of a single geometric morphism. Again, in general, all the sites are going to change. We replace all of them by these oplax limits. All right, I don't want to spend a long time on this because and I'm not even giving all the details on the slide, but the basic idea is we can do something very similar to what we did before. So these new sites, DP, have a forgetful functor down to the original CPs, which have a right adjoint, which is given by taking some finite limits. The right adjoint is fully faithful because if I go up and then I come back down again, that's sort of evaluating this limit in this particular case of identity morphisms. And so the construction basically reduces to taking a limit over a category that has an initial object, which basically just gives back the original object I started from. The same argument as before says I have the presheaves down here are left exact reflective subcategory of presheaves up here. In other words, a subtopos. Then my original topoi are subtoposes of these guys, and so composing that, I get topologies on these new categories DP, whose sites define the original toposes in my diagram. And then I do something similar with the morphisms also. Actually the morphism L is much easier to define. It's basically just on these oplax limit categories, it's composing. All right, so I'm going to map in one direction. I have to evaluate this object at certain morphisms. I just compose those morphisms with my nu and evaluate the object over here. It has a right adjoint, which is defined by finite limits in some complicated way. And there's this square that commutes. And then the same argument applies, basically, that we have these G functors, which are cover preserving. They have left adjoints, which are therefore cover reflecting, and induce the same geometric morphism on sheaves, but on pre-sheaves, they're essential because it's just a composition with a functor, and so it has a left con extension as well as a right con extension. So the conclusion is, if I have a finite diagram of toposes and geometric morphisms, then I can present it by a diagram of sites and cover reflecting functors, which are actually left adjoints. They have right adjoints, which are cover preserving. And then what I can do as I take presheaves on that, I get a diagram of essential geometric morphisms between presheaves. But then I can look at these sort of fancier comprehension categories over them, consisting only of the relative sheaves, and that gives me a way to interpret multimodal type theory in a way that talks about the original categories, the original toposes in diagrams E, but it has these division operations so that we can represent these modalities this way. So that's the big theorem that I wanted to get to. Just to end with a couple of open questions. We don't really know what to do if the diagram is infinite because we used a bunch of limits which are the size of the diagram and they had to be preserved by the inverse image functors as well as the direct ones in the construction. Yeah, it's kind of a problem. If the inverse image functors preserve some extra limits, then we're okay, but they might not in general, so I don't have a good solution to that. I'd like to be able to generalize it to higher toposes as well. At the moment, I only know how to do it in a case where the infinity toposes are one localic, so they consist of infinity sheaves on a one site where we can do the same construction on sites. If we have infinity sites, then it's not clear exactly how to make it work. So this is like open stuff that I'd like to solve someday, or maybe somebody else can figure out how to do it. That's all I wanted to say. There's the paper, which actually, this paper here doesn't actually do the case of toposes and sites. It's just about, it basically says, it's a little bit more general, doing this sort of comma Oplax limit construction directly on the comprehension categories. So that you can do a similar sort of construction that way. But it's got that Oplax limit construction in there if you want to read more about it. And I think I'm done. Thank you.